Quantified modal logic is super important in studying philosophy, but what does it all mean? How do we do semantics for quantified modal logic? Let's take a look. Hello everyone, welcome back to the Attic. Today we're going to be talking about how we do semantics for quantified modal logic. We are basically going to take our semantics for modal logic, our semantics for first order logic, and we're going to smash them together. If you haven't watched those videos, you're not sure what those semantics looks like, go and take a look at those before you carry on with this one. If you're finding these videos useful, you know what to do, smash that subscribe button. So basically what we're going to be doing is looking at the semantics for first order logic, the semantics for propositional modal logic, and combining them. Semantics for first order logic look a bit like this. We draw a diagram where we've got some things, some of them have got a property, maybe some haven't, and there are some relations between those things. Okay, that's first order logic. Modal logic, we also draw a little diagram, but here these blobs are possible worlds. They've got relations between them. These are the accessibility relations. So this world is possible relative to this one. So's this one. This one's possible relative to this one and relative to itself. And we just say, you know, at this world, P is true. At that world, Q is true. Not at that world. So that's the semantics for propositional modal logic. When we do quantified modal logic, we try and smash all of that together. So basically what we're doing is we're trying to put one of these little models inside each possible world in the modal diagram. Okay, so whereas we just had a little blob with no information about it in modal logic, in quantified modal logic, we expand on that. We go inside each one of those possible worlds and we look at how the things are there. We look at the things in those worlds, the properties they have, and the way in which they're related to each other. And we do that for each possible world in the diagram. Okay, once we've got that, that is a model for quantified modal logic. A model for quantified modal logic might look a bit like this. So here we've got a possible world, I've called it S, we've got two things in it, A and B. B's got this property, say being happy, and they're related together. Let's say that A likes B. Over in this different possible world, things are different. Here A's happy but B isn't, and they like each other. I've called this world U. Over in this world T, A's happy, B isn't. A likes themselves but nobody else. And same for B. B likes themselves but nobody else. So it's a kind of really selfish world. And we've also got information about the accessibility relation. Okay, so this world is possible relative to itself and relative to world U. This world and this world are possible relative to one another. This world is possible relative to itself. So what does that mean in practice? Well, when we're working out whether a sentence is true or false, first up we have to look at what goes on inside a world, like who's happy, who likes whom. But we also, if we've got box or diamond in the sentence, we have to think about what's going on in other worlds, and are those worlds accessible from the one we're interested in. So in this world S, A likes B. Okay, that's a fact in that world, but also there's no world that's possible from S other than S itself. So the only possible world is S in which A likes B. So in other words, in all worlds accessible from S, all possible worlds that S can see, A likes B. Okay, so in this world, it's necessary that A likes B. Box RAB. What else? Over in this world U, well, B isn't happy, not FB, but he could be happy because there's an accessible world over here where B is happy. Okay, so we've got B isn't happy, but he could have been. Not FB and diamond FB. Here's another example. In this world, same world, it's necessary that there's something that A likes. Why is that? So to work this one out, first of all, we need to work out which worlds are accessible from world U, so we can work out whether this sentence is true in all of them. Okay, so we start at world U. Which worlds can we get to? World U itself, because there's a loop here. world T, and world S. In other words, all of them. So we're checking, is it the case in all of those worlds that A likes someone? Let's have a look. Over here, A likes B. Over here, A likes B. And over here, A likes himself. So yeah, it's true in each world that A likes somebody or other. So that sentence is true. One little thing to notice here, and this is going to be important later on. We're not saying, is there someone such that A likes them in all worlds? Right? We're just saying, look at each world one at a time. Is there somebody or other in those worlds? Could be a different person each time who A likes. Another example, let's look at this one here. So in this world, world T, B isn't happy. They're not possibly happy because over in the accessible world, just this one, again, B isn't happy. But there is an accessible world from that world over here. In other words, a world that is accessible from an accessible world from here, where B is happy. So an accessible world basically means diamond, diamond. Okay, there is a world I can get to, and then from there I can get to another world where a certain thing is the case. So I go from here to here to here. B's happy here, so back here, diamond, diamond, B is happy. It's possibly possible that B is happy. Okay, so B isn't happy, but it's possibly possible for B to be happy. Now you might be thinking, well, what does it mean for something to be possibly possible? Doesn't that just mean that it's possible? Well, it depends which logical system we're talking about. If you're not sure what I mean by different logical systems, go and look at the video I've done on that. You'll see that there's all these different logical systems. The arrows behave differently in all of them. In the system K4, that corresponds to the arrows being transitive, meaning I can always take shortcuts. If something is possibly possible, that means I can get there in 2 steps, then it's possible I can get there in 1 step. That's not the case in this model because I can go from here to here to here in 2 steps, but I can't go directly there in 1 step. So this model isn't transitive. So all that stuff that we did in the different systems of modal logic, that still applies here. We could talk about whether the accessibility relation is transitive, whether it's reflexive, all of that stuff still applies to here. So have a look at this model. Which kind of system does it belong to? Is it transitive? Is it reflexive? Is it serial? See if you can tell me. Okay, so there's an example of a model. We use those models to give the semantics. Let's go in a little bit deeper and set it out properly. So the official definition of a model is that it's a quadruple made up of 4 bits. We've got a set of worlds. Technically speaking, they can be anything we like, but we think of them as being possible worlds. We've got our accessibility relation. So these 2 bits, they're just the same as what we would have in propositional modal logic. We've got a domain of things. These are the things that we're talking about that have properties or relations to one another. And we've got an interpretation function. This is what pins our language onto the bits in our models. So these 2 bits, they come from propositional modal logic, and these 2 bits, these come from first order logic. Put them together and you've got a model for quantified modal logic. So we use these models to say when a sentence is true or false relative to a possible world in a model. So we read this thing as saying sentence A is true at possible world S in model M. How do we define that relation? Well, we basically just cobble together all of the stuff that we used previously. So if A is an atomic sentence, like A is happy, or A likes B, or A is identical to B, we're going to treat it just like we did in first order logic. If it's one of the connectives, we just do it like we did in propositional logic. If it's a modal sentence, box A or diamond A, then we're going to treat it just like we did in propositional modal logic. And if it's a quantified sentence, everything A or something A, then we're going to treat it just like we did in first order logic. Okay, so if you're interested in exactly how that definition goes, just go back to those videos. We talk about it in more detail there. So one thing I should make clear at this point is we have presented one particular semantics for quantified modal logic. There are different approaches. The one that we've talked about just now, it's called constant domain semantics. Okay, that's going to be important later on. What's constant domain semantics? Well, it's where we have one domain and we use that domain for every possible world in the model. So the domain is the things that we're talking about, and in a constant domain model, we're basically saying the same things appear in every possible world. We're always talking about the same things. So to see what that looks like, let's go back to the model that we looked at previously. In each possible world, we had these two things, A and B. There's no variation there in the things that we're talking about across the different possible worlds. Okay, so there are advantages and disadvantages to doing things this way, both logically and philosophically. In logical terms, the advantages of constant domain semantics, well, it's the simplest semantics. If we deviate from constant domain, things are going to get tricky. It also gives us the most straightforward combination of first order logic and modal logic. We can basically push together first order logic and propositional modal logic and just add a little bit about how the modalities and the quantifiers interact. We're going to get onto that in the next video, and that gives us the logic of constant domain semantics. If, however, we want to fiddle with things so that we don't have constant domains, we allow the things we're talking about to vary across the possible worlds, then it's not just a case of adding together first order and propositional modal logic in terms of what's true, what's logically true in both of those kind of logics. We're actually going to lose some of that stuff. So in that case, there's going to be stuff that might be true in first order logic that isn't true in quantified modal logic. Okay, so things are going to get tricky if we don't have constant domain semantics. On the other hand, it looks like there are good philosophical reasons to reject constant domain semantics. So think about this model here. Let's go to this world here. We're basically saying whatever exists in that world, A and B, exists in all the worlds, and whatever happens in all worlds is necessarily true. So we're basically saying if something exists, it necessarily exists. And we don't just get that de dicto, we get that de re. In other words, for each thing there is, it exists necessarily. It's essential that it exists. And that sounds a bit weird. It's kind of like meant to be this godlike property to exist essentially, of necessity. Whereas most things like you or me, we exist, but we might not have done. There also, it seems, might have been more things. Okay, so I don't have a sister, but I could have had a sister. That might be an argument for thinking that there could have been things existing which don't in fact exist. If you find those kind of arguments persuasive, then you're getting pushed philosophically towards variable domain quantified modal logic. And there things are going to get a bit trickier. So I'm going to leave it on that philosophical cliffhanger. We've got this nice semantics for quantified modal logic, the constant domain semantics, but it seems like there's philosophical reasons that it's not quite going to work. Okay, so what are we going to do about that? Well, we're going to be talking about that in the next couple of videos. If you want to find out about those videos, subscribe to the channel, hit the bell icon to get updates. Thank you so much for all your support. I really appreciate it. I will see you guys next time.